Hey everyone, this is Dr. Walker. This is video 525, electric potential due to point charges. In video 520, I briefly introduced this topic of the idea that charges do produce potentials at a point, and I just gave you the equation for it, but in this video we're actually finally ready to derive this equation to find the potential due to not just one charge, but several charges as well. So let's start by looking at the potential due to just one point charge. We just learned in the previous video that the potential difference between 2 points, and in this case, let's look at the potential difference between points A and B here that are different distances from the point charge Q that is right here in the center. We just learned that to find a potential difference between 2 points, that we integrate the electric field, E dot ds. And there was a negative here, and you just go from A to B if that's what you want to do, find a potential difference between A and B. So let's kind of look at and make sure we understand what this picture is saying here. So what this picture is showing is that a point charge definitely produces an electric field. So there's an electric field produced at point A, and we have the position vector from Q to that point, and then there's a different electric field produced at point B. There's a different electric field produced at every single point, and we are looking at one certain point over here, for instance, and then we will integrate from A to B along whatever path that we want to go to find that potential difference. So we want to integrate the electric field, but we know that the dot product gives us the component of the field that is in the same direction as ds, or in other words, the component of ds that is in the same direction as the field. We know that the electric field is equal to kq r squared in the r hat direction. So r hat is outwards away from the charge. We could also draw it here so we can see it a little better. R hat is going in this direction here. So at this point here, we can see that the dot product of the electric field, so let's go ahead and write down the electric field, kq over r squared, r hat, dot ds. So the dot product of r hat and ds gives you the component that is along this r direction here, ds cosine theta, which we can just write as dr. dr equals ds cosine theta. That's the dot product. So it shows us how much of the ds path is along the radial direction. So now that we know that, we can go ahead and simplify this, and the limits of integration, we're still going from A to B, but now that we're going to change it to kq r squared, and then this dot product here is equal to dr. So now we want to integrate in the r direction. So we can say that we're going to integrate from, let's say, RA to RB, where RA is this position here and RB is that position here. Okay, so we're almost done. Now that we find this integral, we're going to get negative kq over r. So the negatives will cancel out, and we'll be getting ke q over r from RA to RB. Again, the negative from the integral will cancel out this negative right here. And so we get KEQ times 1 over RB minus 1 over RA. So this is the potential difference between the 2 points A and B. And we can see that it's independent of the path, because if we had taken another path, right, well, that dot product is always going to give us that component of the path that is along the RS direction. And if we're going to the same points, that dot product is always going to be the same. So that being said, we like this expression for potential difference, but we're trying to find the potential at one point, not the potential between 2 points. So what we often do is we take our reference point of the potential equaling 0 when you're really far away. So let's say that point A is really, really far away. Let's say that point A is over here. All right. So the distance RA is equal to infinity. So when we have our reference level at infinity, then we can see that the potential, in this case the potential at this point, which is any arbitrary point, is going to equal to KEQ, and we can just call it R, right? It can be any point a distance R away with a reference level at infinity, since this cancels out. 1 over infinity is 0. So this gives us our final expression for the potential due to 1 point charge, where we have taken the reference level that the potential is 0 at infinity. And the last thing we can do is we can expand this to the potential due to multiple point charges. And all we have to do, since potential is a scalar, is we just add the potential due to each charge at that location. This is very similar to when we were finding the potential energy of several charges. We just added up all those energies together. So here, if you have more than 1 point charge, you just add up all of the potentials. The great thing about this is that it's not a vector, so you don't have to pay attention to direction, so it's a lot easier to find a potential due to a bunch of point charges than, say, to find the electric field due to point charges. So that's all for this video. We will do an example in the next video.